This is a TYBSc Topology lecture, and we are learning Unit 2 chapter Sequence in a Metric Space. Now, here we have already learned what is a convergent sequence. Suppose XD is a metric space. We know a sequence is a function from the set of the natural number to the set X. A sequence is a succession of points in the set X. Now here a sequence Xian converges to X belong to X. If for any given epsilon greater than 0, there exists n0 belong to n such that n is greater than n0 implies distance between x and x is less than epsilon. This is how we define the convergent sequence. Now here we will prove a theorem. theorem Let x d1 and y d2 be metric spaces. Let x d1 and y d2 and y d2 x d1 and y d2 be metric spaces. Be metric spaces. Here theorem, let x d1 and y d2 be metric spaces. Let the product metric on x cross y be defined as let the product metric on x cross y be defined as be defined as d x1 y1 comma x2 y2 is equal to maximum of d1 x1 x2 and d2 y1 y2 is equal to maximum of the set d1 x1 x2 d1 x1 x2 comma d2 y1 y2 d2 y1 y2. Let xn yn belong to x cross y be a sequence in x cross y, be a sequence in x cross yd, in the metric space x cross yd, then xn comma yn, then xn comma yn converges to x comma y if and only if and only if and only if xn converges to x in x d1 and yn converges to y in d2 y d2. Now see this theorem. See here, suppose x d1 and y d2 be any two metric spaces. Let the x cross y. See here, x cross y. It is the set of the element of the type x comma y, such that x, small x belong to capital X and small y belong to capital Y. See here, x cross y. X d1 is a metric space, y d2 another metric space. Then we know that x cross y, the Cartesian product of the set x and the set y, it is the set of the ordered pairs of the type x comma y, where small x belong to capital X and small y belong to capital Y. Now we can make x cross y metric space. Therefore the metric defined on x cross y is called as a product metric, and it is defined as d distance. D is a product metric on x cross y, then d distance between the point x1 comma y1 and x2 comma y2 is equal to maximum of the set d1 distance between the point x1 comma x2 and d2 distance between the point y1 comma y2. See here x1 belong to capital X, x2 belong to capital X, and d1 is a metric on capital X. Therefore d1 distance between x1 and x2 is well defined. Similarly, d2 distance between y1 and y2 well defined. Now the theorem is that let xn comma yn belong to x cross y be a sequence in x cross yd in the metric space x cross yd. Then xn comma yn, then the xn comma yn approaches to x comma y if and only if xn approaches to x in x d1 and yn approaches to y in y d2. This is the theorem. See here theorem. If x d1 and y d2 are any metric spaces, the product metric defined as d x1 y1 comma x2 y2 maximum of d1 x1 x2 comma d2 y1 y2, then the sequence xn comma yn in cross y approaches to the point x comma y in x cross y if and only if xn approaches to x and yn approaches to y. Now we will prove this theorem. Now see here, Proof of the above theorem. Proof. Here, proof. Let x d1 and y d2, capital Y d2, be any two metric spaces. Be any two metric spaces. Two metric spaces. Then x cross y, the Cartesian product of the set x cross y, it is the set of the small x comma small y such that small x belong to capital X and small y belong to capital Y. See here. Then x cross y, it is a set of the type element x comma y so that small x belong to capital small x belong to capital X and small y belong to capital Y. Now d from x cross y cross x cross y cross x cross y to R is defined as defined as d x1 comma y1 comma x2 comma y2 is equal to maximum of the set d1 x1 x2 d1 x1 x2 and d2 y1 y2. See here, d distance between x1 y1 and x2 y2 is defined as the maximum of d1 x1 x2 and d2 y1 y2. See here, now later xn comma yn belong to x cross y approaches to xy in x cross y. See here, later xn comma yn belong to x cross y d. This is a metric, product metric. It is called as a product metric space. Approaches to x comma y in a product metric space x cross y d. See here, then we prove that xn approaches to x in x d1 and yn approaches to y in d1. Now see here, since xn yn, which is a sequence in the metric space x capital X cross capital Y d, this sequence approaches to the point x comma y in x cross y d. Therefore, now here we prove that the sequence xn approaches to the point x in x and the sequence yn approaches to the point y in y d2. Now, therefore, for any given epsilon greater than 0, for any given epsilon greater than 0, here हाँ लेट xn comma yn ठीक है approaches to x comma y. Let x and yn in x cross yd approaches to the point x comma y in x cross y d. Here, therefore, for any given epsilon greater than 0, for any given epsilon greater than 0, there exists a n0 belong to n. There exists a n0 belong to n such that n is greater than n0. N is greater than n0 implies here since xn approaches to x cross y for given epsilon greater than 0, there exists n0 belong to n such that n is greater than n0 implies d distance between the point x comma y xn comma yn and x comma y is less than epsilon. Therefore, n is greater than n0 implies d was here d. How do we define the d distance between x and y and x and y? It is equal to maximum of the set d1 xn x and d2 yn y. d2 yn y is less than epsilon. Here, therefore, n is greater than n0 implies maximum of the set d1 xn x and d2 y1 y is less than epsilon, and therefore n is greater than or equal to n0 implies d1 xn x. Here, maximum of this is less than epsilon. Now, therefore, d1 xn x is less than or equal to maximum of the set d1 xn x comma d2 yn y2. Therefore, n is greater than n0 implies d1 xn x is less than epsilon and d2 yn comma y is less than epsilon. This means xn approaches to x in the metric space xd1 in xd1 and yn approaches to y in yd2 Therefore, as xn yn approaches to x comma y, here let xn comma yn approaches to x comma y. Therefore, for given epsilon greater than 0, there exists n0 belong to n such that n is greater than n0 implies d distance between x and yn and x comma y is less than epsilon. Therefore, n is greater than n0 implies maximum of the d1 distance between x and x and d2 yn is less than epsilon. Therefore, n is greater than n0 implies here this maximum of the d1 xn y x and d2 yn y is greater than or equal to d1 xn x is less than epsilon, and therefore here d1 xn x is less than epsilon and d2 yn y is less than epsilon. Therefore, xn approaches to x and yn approaches to y.
कॅश पार्सल नाही, ऑनलाईन पेमेंट केलेलं आहे ॲप्लिकेशन. एकदा कन्फर्म करा तुम्ही ऑनलाईन पेमेंट केलेलं आहे.
Conversely, 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 suppose xn approaches to xn approaches to small x in the metric space x d1, and yn approaches to y small y in metric space y d2. Here we prove that the sequence xn comma yn approaches to the point x comma y in the metric space x cross y d, where d is a product metric on x cross y. Here, therefore, for any since xn approaches to x in the metric space x d1, for any given epsilon greater than 0, for any given epsilon greater than 0, there exists n1 belong to n such that n is greater than n1, such that n is greater than n1, n is greater than n1 implies d1 distance between x and x is less than epsilon, and there exists n2 belong to n such that n is greater than n2 implies d2 distance between y and y is less than epsilon. Here, since the sequence xn approaches to small x in the metric space x d1 and yn approaches to small y in the metric space y d2, therefore for any given epsilon greater than 0, there exists n1 belong to n such that n is greater than n1 implies d1 distance between x and x is less than epsilon, and there exists n2 belong to n such that n is greater than n2 implies d2 distance between x and y is less than epsilon. Let n0 is equal to maximum of the set n1 n2, maximum of the set n1 n2. Let n0 is equal to maximum of the set n0. Therefore n is greater than or equal to n0 implies maximum of the set d1 xn x and d2 y2 and y and y is less than epsilon. Here n is greater than n0. Therefore d1 xn x is less than epsilon and d2 y and y is less than epsilon. Therefore maximum of the set d1 xn x and dn y and y. Therefore d distance between n is greater than n0. Therefore d distance between the point xn yn and x comma y is less than epsilon. Therefore that mean is less than epsilon. Here, therefore d distance between the point x and y and x is less than epsilon. Therefore the sequence xn comma yn approaches to x comma y in x cross yd in x cross yd. Now here in this here now we now Cauchy sequence. Let XD be a metric space. Let XD be a metric space. XD be a metric space. Space. Let XD be a metric space. A sequence Xian. A sequence. A sequence Xian. N belong to N is said to be a Cauchy sequence. Is said to be a Cauchy sequence. To be a Cauchy sequence if for any given epsilon greater than 0, if for any given epsilon greater than 0, for any given epsilon greater than 0, there exists n0 belong to n, there exists n0 belong to n such that n comma m is greater than or equal to n0 implies distance between x and xm is less than epsilon. Now see here, suppose xd is a metric space and the sequence xn is a sequence in x, then the sequence xn is said to be a Cauchy sequence if for any given epsilon greater than 0 there exists n0 belong to n such that nm is greater than n0 such that distance xn xm is less than epsilon. Means in metric space xd a sequence is Cauchy if its terms are as near to as near as we wish after a certain terms. Such a sequence is said to be Cauchy sequence. For example, let xd is equal to ru. Let xd is equal to ru, the set of real number with the absolute value metric. Let xn is equal to 3 upon 4n plus pi. 3 upon 4n plus pi. We prove that the sequence xn is a Cauchy sequence in Ru. We prove that the sequence xn is a Cauchy sequence in Ru. See here, uh, now 3 upon 4n plus pi, 3 upon 4n plus pi is less than 3 upon 4n is less than 3 upon n. Here 3 upon 4n plus pi is less than 3 upon 4n is less than 3 upon n because 4n plus pi is less than greater than 4n. Therefore for any given epsilon greater than 0, for any given epsilon greater than 0, there exists n0 belong to n such that 3 upon such that 1 upon n0 is less than epsilon by 3 is less than epsilon by 3. 1 upon n0 is less than by epsilon by 3. Therefore, so when n m is greater than or equal to n0 imply n m is greater than or equal to n0 implies 3 upon 4n 3 upon 4n plus pi is less than 3 upon n is less than 3 upon n is less than 3 upon n0. 3 upon n0 is less than epsilon and 3 upon 4 m plus pi, this is also less than epsilon. Therefore 3 upon 4n plus pi is less than epsilon and 3 upon 4m plus pi is less than epsilon. Therefore n is greater than n, m is greater than n0. Therefore, n m greater than n0 implies 3 upon 4n. Here 3 upon 4n plus 5 is equal to xn. xn belong to open ball 0 to epsilon, and xm also belong to open ball 0 to epsilon. 0 to epsilon. Therefore, n m is greater than n0 implies distance between xn and xm is less than epsilon, and therefore xn is a Cauchy sequence in Ru. xn is a Cauchy sequence in Ru. Therefore, xn is a Cauchy sequence in Ru.